Welcome to lecture 15. In the last class, we have discussed and derived the continuity of flow equation along with the Darcy's law, and we get the equation governing seepage, particularly for it's a two-dimensional flow. We have derived the governing equation for what we call as homogeneous soil, which means permeability K is constant, does not depend on distance, whether it's x coordinate, y or z coordinate, but K need not be same in the three directions. So we derived it for two-dimensional case. Again, I would like to mention it is a steady seepage condition, which means quantity in is equal to quantity out. So if you take a small element or any element, what you are saying is the flow can enter in two directions and it will go in the two other planes. So this Q1 or Qx, QZ prime and Qx prime. So Qx plus Qz is equal to Qz prime plus Qx prime. That is what you say as a continuity condition. So please remember, like in all fluid mechanics, continuity condition is being satisfied, because of which we get the simple governing equation Kx into second derivative of the head or potential plus Kz into delta square h by delta z square is equal to 0 for a two-dimensional problem. We normally in this course do not concern ourselves with three-dimensional one, but if you do have a three-dimensional flow, this equation will get changed to one more term. We have the derivative with respect to y apart from the two derivatives. For isotropy, which means Kx is equal to Kz, and if you have three-dimensional, it's equal to Ky. This equation becomes very simple. This is called Laplace equation. Now, how to solve this equation? We have different approaches. As you can see, it's a fairly complex one. So, analytical solutions is one possibility. They are very complex, or we had to use complex numbers and complex equations, etc. So, we have very few standard solutions. The second most popular now with all the good computers are the numerical methods, where we have what we call as finite difference method, finite element, and boundary equation method. These are fairly easy, and particularly the first two, you get very good standard packages. In your computer applications course, probably you will be able to use them. And if time permits, tomorrow in the next lecture, I would like to introduce you to the finite difference, which is very easy and you can use a lot of hand calculations. The third most common method is what you call as flow nets, which we'll be discussing now. And the fourth one is the analogies. Analogy, we can say physical, and we particularly try or apply electrical analogy. Just to give you an idea how analytical solution is used, I'll just give two solutions which have been obtained. For example, let us say you have a pervious stratum. This is impervious, this is a sand stratum, so has high permeability. You want to build a reservoir. So what earlier was done was, when they had a lot of cheap steel material, you could have a sheet pile and then you can store water here. And on the downstream side, maybe the water level is slightly above the ground, but upstream you are able to store up to a height h. You are able to prevent the water from flowing across above the ground, but is there a way in which we can prevent it? So to prevent that, we sometimes drive a sheet pile. Nowadays we have what they call as diaphragm walls too, or cut-off walls. Let's say the thickness of this stratum is T. How deep should I drive the sheet pile or install the cut-off wall, and what will happen to the discharge? So for that, we analytically can get a simple solution, and then if you write the discharge divided by K into H, the normalized parameter, say it varies from something like 5 or 10 here, and here I am plotting S by T, and I put 0 to 1. You can see that S by T gives me what is the relative depth up to which we had to drive the sheet pile with respect to the thickness of the stratum. If S is 0, there is no sheet pile below the ground level. When S is equal to T, when the ratio is 1, you are putting a complete cutoff, and you get an analytical solution where the curve drops down from a very high value to practically 0 when you put the whole thing. Now, this is used in our engineering solution, saying that how much loss can I afford to allow, so that if I know I can reduce the seepage into the downstream side, the amount I say is acceptable, then I decide how much will be the penetration into the ground with respect to the total depth. Similarly, if you have instead of a sheet pile, let us say you have something like our original Godavari Anicut or the barrage, Krishna barrage at Vijayawada, what they call as Prakasam barrage. You have a profile something like this, let's say, and then you want to store water, and here is the downstream side. Or you can change this to, instead of capital H, use small h. So discharge, rate of discharge by coefficient of permeability into the net head. Similarly here, I have H. Now the width of the Anicut is B, and if I look at the center point, this is B by 2, half the width. Let's say you call it as small b, and you want to put a cutoff now below the Anicut or the barrage, and again this is the bottom of the sand stratum, which is resting on an impervious bed. Now we would like to know which is the best place to keep this from the center, and this depth is S and this is T. Where should the cutoff be placed? I can put it at the extreme left, in which case x is equal to half the width, small b, or I can put it right at the center, in which case x will be 0. Again, we have some standard analytical solution for this, according to which we have q by kh against, here I am plotting x by, say, b by 2. And you get a series of curves depending on the ratio. S by t, let's say, is 1/3, and b by t is equal to another value, which means It also depends now on the width of the B or B by 2. So for various combinations, say this is 2. If I have a very wide barrage or I have a narrow one, so S by T is equal to 1/4. This is 2. Then I can have S by T equal to 1/3. But B by T is now 1.5 or 2.5. So we have the standard solutions which are available in the book, and one can use it to decide where should I put the cutoff with respect to the center of the barrage. So these are the kind of designs you do as a civil engineer using analytical solutions. But as I said, there are very few standard analytical solutions, and these days we are using either finite difference method, finite element, or the flow nets. The other method which you may do in the laboratory is analog, wherein, as I said again yesterday, the flow through soil, which we call as seepage, is very similar to flow of current through a conducting medium or flow of heat. And we use this usually. You take a conducting medium, let's say I take a copper sheet, and if I want to simulate the cutoff, I simply tear it or use scissors to cut it so that there is a small gap here. And then I'll take a battery and connect it here. So you have the positive and the negative nodes here, and the voltage will flow along this. And the equation is exactly the same. Instead of H, we'll have and so by measuring the potential, I can get the solution. So this is an experiment we can do in the laboratory, either using a conducting sheet, or usually we have carbon coated ordinary paper. You take a sheet of paper and then get it coated with carbon and use this itself. So in order to provide the cutoff, what we do is we simply tear it so that across the tear the power current will not travel or it's not transmitted. So that is a very powerful method. But let's go to one of the most simple, elegant methods which all of us can do, and it needs a little practice, and those of you who are good at sketching can do a very good job. I call that as flow nets method. It consists of two lines. What are the two lines? One is called the flow line and the other is called the equipotential line. What are they? The flow line is the flow or the path taken by a water particle. It travels from upstream to downstream side. Let's again look at our simple standard problem. I have a pervious stratum here, sand with some permeability, and you are storing water up to here. And this is the downstream side. Let's say the water level is at the ground level. This is the same as ground level. Now imagine or visualize what will happen to a soil water particle just to the left of the sheet pile. Because the head here is high, the net head difference is h, so there has to be flow. If there is a flow, how can this water particle or molecule travel from upstream to downstream? Obviously, you will say it will come along the sheet pile, go back and go downstream. Is there any possibility, any other possibility for the flow? Obviously, it cannot go across the sheet pile, which is a metallic obstruction, no flow across that. You cannot have. So it's just like if I have a barricade, I have a table here. If I want to go, I'll have to go around the table to go to the other side. So this is what happens. This is the shortest flow line. Can I say, as far as this is concerned, what will be the longest flow line? Just imagine this whole thing is a large deposit, obviously running into hundreds of meters or 1,000 meters. So the longest flow line would be along the bottom. So you can see that the flow is along a line. Can the lines intersect? Can a flow line intersect with other? Obviously no, because the path has to be a steady state flow, and we are always talking of laminar flow and not turbulent one. Imagine another point somewhere in between. If the water molecule here from this point, let's say I looked at A to B, C to D, it will be parallel to the water surface, CD. Now I am looking at another water molecule starting at point E, and you will realize E to F will have to be something like this. The water molecule will come, the path will be somewhere between the bottom, let's say this is called G, and if I look at this point H, the path will be between J and H. If I take any other point here, K, it will come to L. So you can see now with your simple sketching technique, you can draw any number of flow lines. What are the characteristics? The flow lines will have to generally start on the upstream side, and they'll travel to the downstream without intersecting each other. Second characteristic would be, I'll come to that now, an equipotential line is again from the same concept. Let's now define an equipotential line. What does it mean? Equipotential. The head is the same at every point along this line. Let me look at now the line AB. AB is horizontal and the water level is here. So can you tell me, if I take this itself as my datum, the ground level is taken as the datum. So what happens to the potential? Along A to B, any point I take, the head is equal to, or the potential is equal to H. So H is equal to the head along the line AB. Can you tell me what will be the potential along this line CD on the downstream side? The datum is at ground level, the water level is also at the ground level, so there is no potential at all. So H is equal to 0 along the downstream side line CD. So now can I say AB is one equipotential line, CD is another equipotential line. The potential along AB is constant, equal to H. Potential along CD is constant, equal to 0. And using your principle of symmetry, you may immediately say maybe this line EF through the center of the medium will be a 50% potential. So this is equal to, H is equal to 0. Sorry, I think better not. The potential here, I'll call it as H naught. This is H naught. That becomes, it's a 50%. That means the head loss from AB to EF is 50%, and from EF to CD is another 50%. And again, as practice, we'll now do the in between so that I can get different contours which will give me the head along this, or the potential along this is all constant. So equipotential line, by definition, a line along which the potential, or can we say total head, which is what we call as a potential, is constant. Please remember, these are the two lines which are necessary to plot the flow net. a flow line which is the path taken by a molecule of water while it traverses from the upstream side to the downstream side. The shortest path is just starting to the left of the sheet pile and goes down along the sheet pile, goes round the sheet pile, and goes up along the sheet pile back to the downstream side. The longest flow line starts at infinity, or let's say for us infinity could be 1 kilometer or maybe 500 meters. Start from here, goes along the bottom impervious boundary, along that, because no flow can take place here. As we said, the K of this medium is 0. So if there is no K, there is no flow. So water has to flow along the surface and it will go to the right, maybe another 500 meters or 1 kilometer. And all other flow lines are bounded by these two, shortest and the longest flow line. Similarly, if you look at the upstream surface, upstream boundary, the bottom of the reservoir or the top of the ground is an equipotential line with the maximum potential equal to the head difference or the net head loss between the upstream to downstream side. This is upstream, this is downstream. And you find that this is the 100% equipotential line. On the downstream side, you have the 0% potential line. And using the principle of symmetry, you can immediately say the line through the sheet pile, this is the flow region. From the ground level up to the bottom of the sheet pile, there is no flow across it. So all flow is now concentrated through the gap between the bottom of the sheet pile and the bottom of the pervious layer. And you will see the flow line will be crossing that, and the equipotential line continues below. And this corresponds to the 50% potential line. Flow net consists of these two lines, and the only requirement is a flow line and equipotential line are orthogonal. Please remember, this is the most fundamental one, is perpendicular to. This is a necessary requirement. You can also prove mathematically. It will take few more minutes, so maybe we will not go into that. But I would like to illustrate how, based on this characteristic, we'll try to draw a simple flow net. Let's look at our simple problem. So this is the upstream side and this is the downstream side. You have just now seen that the shortest flow line is this one, or flow path, if you want to call it A to B, maybe through point C. And the longest one is from D to E, along the bottom of the pervious layer. We said the sand stratum is resting on a very hard rock which is impervious. Now let's take a point slightly to the left of point A and try to visualize what would be the flow path. I can draw something like this. I take one more point here and try and another flow line. Now we'll have to draw the equipotential lines. What is the criterion? Equipotential line has to be perpendicular. So can I now start something like this with one more criterion, that it will be nice if these, what you call quadrilaterals, are approximately square, then you get very easy solution. So each, what should I say, the element formed by flow lines and equipotential lines should be approximately a square. I don't mean exact square shape. What I mean is that if I take this distance, let's say I call B, is equal to same. These two, or you can say the diagonals are approximately same. Nearly same, then you get a very good flow net. You can see here each element, as the flow takes place, the size of the element may change, but the shape of the element should be approximately square. As you can see, when I sketched it, this is not a very good square, or this one. So maybe when I'm doing this, I can always erase it and draw, and then I can change it this way. And now you can see this is somewhat better than before. Each time you are looking at these two dimensions, and they should be same. The distances between center points or the diagonal lengths should be same. That we call as a very good flow net. Again, here you can see, maybe I should have done something like this. I get a very good square here, and maybe here I get 2. So by what they call as trial and error method, we can draw the flow lines, flow nets. All that you need is take a piece of paper, use a pencil, draw the sketch, and then if it is not fine, you immediately erase it and adjust the lines so that we get this pattern. I'll show you another flow net for the barrage or the weir. So here is the barrage which you have constructed on a pervious stratum, and you want to store water over a height h0. Now look at the point A, which is just to the left of the barrage, and you will see that the water molecule can go below the bottom of the barrage or the weir, and that will be the shortest path. Similarly, the longest path will be along the bottom of the stratum, where the water molecule will travel from the upstream to the downstream side. And now you can see A to, let's say, C is an equipotential line. This is equipotential line, and B to, this is E, and B to F. This is another equipotential line. What is the potential along A to E? H is equal to H0, whereas along BF, H is equal to 0. I am taking the downstream water level as the datum. Now let us try to visualize what will be the flow paths, and you can see that if I take a point here, it can travel something like this. Take another point to the left of it. So you will get the flow lines, and let us try to draw the equipotential lines. Now you can see that this is one equipotential line, this is another equipotential line. So we have to now draw a set of equipotential lines. Maybe here, and one more here. Now you can see a rough flow net, which is not exactly good because we have only one trail. But I could get some elements which are squarish, because this dimension is same as this dimension. But then some are not squarish. For example, this is a rectangle. So we have to keep adjusting by practice how to get a perfect square. This is not a very good one. So maybe I had to move it here, I'd move this to the right, or in such a way that I get a whole perfect flow net. Once you do that, that's the solution for the problem. And each time you have to make sure these two are always orthogonal. Please make sure that the line here is perpendicular. This angle is 90 degrees everywhere. So you have to keep maintaining a orthogonality everywhere. So when you draw, the requirement is the two lines intersect with each other at 90 degrees, the equipotential line, the flow line, and each element within the flow net is approximately a square. So if I look at this distance is equal to the second diagonal. Another way you can visualize is, can I put a circle which will be tangential to the flow, four lines on either side, the flow lines and the equipotential line. If I do that, then I get a perfect flow net. Here I am saying I am trying to fit in a circle, and that is what gives me a perfect flow net. We will see some examples of that in the presentation, but I would like to stop at this stage so that we discuss more in the next lecture.